The last group of problems in the review relate to limits. And so our first problem is to take the limit of the quantity 1 plus 3x raised to the negative 2 over x power. And in order to do limits involving powers with variables in the base and the exponent, we want to convert this to the exponential function. So 1 plus 3x to the negative 2 over x power is the same as the exponential, base e, of the power, negative 2x, times the logarithm of the base, 1 plus 3x. So in order to answer this question, first we're going to take a limit of what's in the exponent. So the limit of what's in the exponent, the limit as x goes to 0 of negative 2 over x times the logarithm of 1 plus 3x. As x goes to 0, there are two pieces. There's this chunk negative 2 over x. As x goes to 0, that piece is going to go to negative infinity. And then secondly, if I think about 1 plus 3x, 1 plus 3x, as x goes to 0 is going to 1, and the logarithm of 1 is 0. So this is an example of an indeterminate form, but we can't use L'Hopital directly. So it's indeterminate, but not L'Hopital. That's because it's not a fraction. So what we'll do is we'll rewrite this. This is the same as the limit, and we'll just write this fraction so it's negative 2 logarithm of 1 plus 3x divided by x. And this makes all the difference in the world, because now I have a fraction. On the top, I get negative 2 times 0, negative 2 times 0, and on the bottom I get 0. And so this is an indeterminate form, but now I can use L'Hopital's rule. L'Hopital's rule applies. And so I can rewrite this limit now as a new limit using L'Hopital's rule, where I take the derivative on the top and the derivative on the bottom, and now I can calculate the limit plugging in my x as x goes to 0. So x goes to 0 only appears in one spot, and our answer will be negative 2 times the fraction 3 over 1 plus 0 over 1, which gives me a value of negative 6. So L'Hopital's rule tells me that the limit of the exponent is negative 6. So now the limit of the original function, the limit as x goes to 0 plus of 1 plus 3x to the negative 2 over x, must be equal to e to the negative 6th. The second problem, we want to take a limit as x goes to infinity of 2x times the exponential of e to the negative 3x. This is somewhat similar to the previous example. I have a product of 2x, let's not box that, let's just underline it, of 2x and an exponential. And if I thought about what happened to those pieces, 2x goes to infinity, but e to the minus infinity, that's infinity times 0. So that's indeterminate. In order to use this, I really need to put it in a fraction form so I can use L'Hopital's rule. So that exponential naturally fits e to the negative 3x is the same as dividing by e to the positive 3x. And now I have a limit where the numerator goes to infinity and the denominator goes to infinity. So L'Hopital's rule applies. And L'Hopital's rule is what justifies me in writing a new limit as x goes to infinity with a new formula coming from the derivatives of the top and the bottom. Now this time I get a number 2 on top and an infinity on the bottom, A number divided by infinity gives me a limit of 0. So that's the answer to the second question. For the third limit problem, we take the limit as x approaches 3 of the exponential base 2. So it's 2 to the x minus 8 over x minus 3. So the first thing we try is what happens if I plug it in. So if I do 2 cubed minus 8 over 3 minus 3, I can see that I'm getting a 0 over 0. That's a L'Hopital style problem, so L'Hopital's rule applies. And I can rewrite this limit as a new limit as x goes to 3, where I take derivatives of the top and the bottom. 2 to the x. It's an exponential, but it's not base e, so I have to remember the logarithm of 2. And the derivative of 8 is 0, so I don't have that term. In the denominator, I have just a 1. And now, if I plug in 3, there's not going to be any issues. The answer will be 2 cubed times the natural log of 2 over 1. So that's 8 natural log of 2. Now in class we learned an alternate approach. Let me just illustrate how that would work. I could make a substitution that u equals x minus 3. And if u equals x minus 3, because x approaches 3, that implies that u must be approaching 0. And every x that I see in the formula must be replaced by u plus 3. So the limit as x approaches 3 of 2 to the x minus 8 over x minus 3 can be replaced with our substitution as the limit u goes to 0, 2 to the u plus 3 minus 8 over u. Now I'm going to use the properties of exponents, and that 2 to the u plus 3 becomes 2 to the u times 2 cubed, which is 8, minus 8 over u. U goes to 0. And if I factor out that 8, I get a limit 8 times 2 to the u minus 1 over u. U is going to 0. This limit we learned, as u goes to 0, is the logarithm of the base, logarithm of 2. And so the answer must be 8 natural log of 2. So we could have done it directly, like I just did, or we could have used L'Hopital's rule. The fourth problem in this limit section is to calculate the limit as x approaches 0 of the sine of 4x over x. So, well, the first thing we do is we try to just plug it in. So I would say, well, what's the sine of 0 over 0? Well, the sine of 0, unit circle, that's 0. 0 over 0. This is indeterminate, but it's L'Hopital indeterminate. But L'Hopital's rule applies. L'Hopital's rule allows me to rewrite it. And so I can replace this limit with a new limit as x goes to 0, where on the top and bottom I replace it by the derivative. So the derivative of sine is cosine, the derivative of 4x is 4, and the derivative of x is 1. And now I can plug in my value 4 times the cosine of 0, and the cosine of 0 is 1, so I get 4 times 1 over 1. The answer is 4. The fifth problem in the section says we want to take the limit as x approaches pi over 3 of sine of x divided by 2 cosine of x minus 1. So, well, the first thing we always try on a limit is find out what happens if we just plug it in. So we get the sine of pi over 3, and in the denominator we'll have 2 times the cosine of pi over 3 minus 1. And let's see, pi over 3 is 60 degrees. So here's 60 degrees. The short side and root 3 over 2. So by the triangle that we remember, the sine of pi over 3, that's root 3 over 2. And the cosine, so we get 2 times a half minus 1. I can see that I've got a number, root 3 over 2 over 0. Now, this is not indeterminate. So we do not use L'Hopital's rule. Do not use L'Hopital's rule. Because L'Hopital would only be if it's 0 over 0. Instead, what we know is this is an infinite limit, and we'll have to check the two sides. We need to figure out, is it positive or negative? So let's check the sides. Well, we need to figure out where this function can change sign. So sine of x can equal 0. Let's think unit circle. Throw a unit circle up there. Sine equals 0 when the y is 0. Okay, so 0 and pi. And then secondly, the cosine, 2 cosine of x minus 1 equals 0. Add 1 and divide by 2. So cosine of x would have to equal a half. And again, so let's think about that on the unit circle. We've got, oh, that's awful. So is that. Come on. There we go. Cosine of x equals a half. We have angles here that look like pi over 3 and negative pi over 3. Now all we need is we need the angle close to pi over 3. So if I'm going to do my sine analysis is of sine of x over 2 cosine of x minus 1. The angle we care about is here at pi over 3. And we learned that we have to worry from 0 to pi. And those are the only points that where it can change sign. Now, beyond that, I have infinitely many points, but I just need to worry about these two signs. So we're undefined at pi over 3. That's because we divide by 0, as we saw above. And we're 0 at these 2 points, at 0 and at pi. So we need to pick points in between. For example, pi over 6. And if I plug pi over 6 into my formula, sine of pi over 6 will be a positive number. So that will be positive on top. And what happens to the cosine? Well, the cosine of pi over 6. The cosine of pi over 6 is root 3 over 2. Double that, so let's see. Let's just write this down. Sine of pi over 6 over 2 cosine of pi over 6. I don't think you'd be able to follow my argument. So sine of pi over 6 was a half. We get 2 times root 3 over 2 minus 1. And so root 3 is greater than 1, so that's going to be positive. So it's positive over positive. So I get a positive value on this side. I might try something over here like pi over 2. Do 90 degrees, those are easy. So the sine of pi over 2 over 2 cosine of pi over 2 minus 1. This is going to be 1. The cosine of pi over 2 goes away, and so I get a negative value. Alright, so on the left, I'm positive. And on the right, I'm negative. And I can use that information to finish answering the question about the limit. And I'm going to have to clear a little space. And now I can draw my two sides. So in red here, I'll write the limit. As x approaches pi over 3 from the left of sine of x over 2 cosine of x minus 1, we saw was positive, so we get positive infinity. On the right, we would write the limit as x approaches pi thirds from the right of the same formula, sine of x over 2 cosine of x minus 1. That was negative on the left, on the right. And so these are my answers. They're different. So the limit that we originally wanted doesn't exist. But these two parts are essential. The limit does not exist. If I didn't say what the value of the limits on the sides were, I would be incomplete. Well, that finishes the last section of the test review.